Okay, welcome back, dear friends. This is Ibrahim Amir Moaire, and today, of course, we are back to discuss, as usual. Our area is technology, and today specifically, I want to talk about the introduction to the fundamentals of AI. Of course, we have limited time, so we are going to try to be as faster as possible. Yeah, because what we are going to summarize, despite the time aspect, would have taken a full day describing these concepts, but let us try to be as faster as possible. So we want to discuss 9 modules today, right now, and we are going to be as faster as possible. Of course, this is how it is going to work. We are going to describe a model, then we talk about the different intelligence aspects in that model, and we show the data mining link, of course, contained in that model, and we show how that module is related to the project. And of course, our project for today that we are aiming at, it is going to be about sugar detection, diabetes diagnosis. Yeah, so that will be it. But because of time, I may not be going through the intelligence aspects and the data mining link. Of course, that I think we'll be able to see, and you catch up with me. So I'm going to put our emphasis on the concepts contained in each of these modules. I think we are okay and clear. So our first module, we are talking about the artificial intelligence, its history, trends, and the future. Yeah, of course, artificial intelligence, as we all know about it, that is a field. It is a field that is devoted to building artifacts capable of displaying behaviors we consider to be intelligent. So under artificial intelligence, we want to develop machines, systems that display behaviors, and those behaviors are considered to come from something which possesses intelligence. And when we talk about intelligence, we mean, first of all, learning. Something to be considered intelligent, it should be capable of learning, should be capable of solving problems and adapting to changes. So that field that is there to develop such systems that can learn from experience, that can adapt to changes and are capable of solving problems. So that field is what we call the AI. Of course, AI has been evolving a long period of time, over a long period of time. Of course, it started long time ago. I think that was around 1940 something, when we had Leonardo, that famous artist. All of you, I think you know him. That guy designed a knight. Yeah, it was a robot in form of a knight. I didn't want to call it a robot because by that time even the term robot was not there, but he designed that artifact. It was in form of a knight that was capable of imitating the human body movements. Yeah, but of course all of that was based upon the pulleys, on the pulleys that were connected to that robot. So it was capable of moving the joints and so on. Of course, that was not AI, but it was an indicator that in the near future maybe we could have systems that are capable of doing so. Then we came to see the Frank. That guy, it was around the 1907 when he published a story, and it was called the Master Key. Yeah, I think it was called the Master Key. And in that story, of course, there was an illusion of, in the near future, having intelligent systems. Of course, what he named the demon of electricity. So it was an indicator that maybe in the near future we could have machines that are capable of imitating and interacting with the humans, of course. Then in the 18th century, we come to see the dark, the chess playing, automation. Then we come to see the checkers machine that was capable of even defeating the humans in chess playing, and it was a machine. So we see how this AI system, this AI field has been evolving over time. Then we come to see the Turing test from the Alan Turing. We have mentioned that lot of times. Then after that we come to see the symbolic AIs and the expert systems. Here when now the systems started to be coded, but of course using hand coded system, that if this then you do this, if this then you do this. So systems were capable of solving problems but using the hand coded rules and algorithms, so they could not adapt and learn from the environments. Now after that we come to see the statistical AI and the machine learning, where now these machines were capable of learning, not being hand coded. I think you see that. Then you have the deep learning and so on. So that is a simple introduction to the AI and its trends over time. So that is the same with the project that we are working upon maybe, and that is, as I mentioned, the Sugar Scout, which is trying to diagnose to see whether a patient has diabetes or not. Yeah, so our second module is the introduction to problem solving. Problem solving is just simply the method or the way of finding sequence of actions from the initial to the final state, given the problem description and the possible actions. Yeah, problem solving, under here from this definition we can see a variety of concepts. We have what we call the initial and the final states. So we have an initial step that we want to convert, to convert to a desirable final state. So the sequence of actions we take is what we call problem solving. So you are at home, you want to go at your place of work. So the initial state is you being at home. Then the final state, you want to arrive at the workplace. So the sequence of the action that we are going to take to take you from where you are to your final state, that is what we call, that process is what we call the problem solving. So problem solving, of course, we have the initial state, we have the operators and the goal state. So the operators are the different actions you have to take. For example, you have to take a jig, you have to take a car, you have to get the transport and so on. So all of those are what we call the operators. So if you look here, we have a number 2 and 3. So you can say that that is our initial state. So the operator, there can be different operators. You can have an addition, subtraction, power, and so on. So if we have an addition, so that is an operator. Then the final state is what we are going to arrive at after summing up 2 and 3, for example. So in AI, we have what we call an AI technique, and that is a method of exploiting knowledge from the given knowledge that can enable us solve a given problem. So wherever we have a problem and we want to solve it, so we have 4 series, we follow a 4-series loop. First of all, we need to define the problem. I'm at home, I want to go, I want to reach to my workplace. So we analyze that problem. So what are the different possible solutions, action that you can take to make you arrive to your desired goal? Then we represent that task, we represent the task knowledge. Yeah, so I see that I can take this route, I can do like this, I can do this. So we represent that, yeah, as we are yet to see on knowledge representation. Then after representing the task knowledge, then we choose the best alternative among those. So here, of course, in our system, so the initial state is the parent is raw data, that we have your heartbeat, we have your weight, and so on. So the operators we have, as we said, the action that can be taken from the initial state to the final is data processing, of course. So we process that data, the AI, the model is going to process that data, and the goal, the final state we want to arrive at, is to predict whether you have diabetes or not. Yeah, so if we proceed, we have problem solving by search. As we said, that problem solving just transforming from the initial state by applying different actions to arrive to the final state. So we have various methods we can use to solve the problems, but now I want to see problem solving using search. If you are sick, we don't want to search. Your problem, you are sick, so the solution to that is taking tablets, so the problem will be solved. But now we want to see how can we apply search in order to solve problems. Our problem may need some bit of searching in order to arrive at the final goal. And of course, under searching, we have two different types of search. Mainly, we have what we call the informed search and the uninformed search. When we talk about the uninformed, sometimes we call it the blind search. Why do we call it blind? This blind search, it uses no prior knowledge about the problem it is solving, such that it can arrive at the final goal in the shortest time possible, but rather it just carries out follows the procedures it should take up to it arrives at the solution. It uses no prior knowledge about the problem it is solving. That is why we call it blind. So we have algorithms like the deep first search, we can use the breadth first search, and I think you are aware about those. Okay, if the terms are new to you, we have our sample tree here. We have a tree, we have, take an example that we are looking for 14, for example. If it is a depth first search, it has to first go as deep as possible until it finds a dead end. So it will search from the root that is 11, then it takes this direction to 7, after that it goes to 5, after that it goes to 3, and so on. So after finding a deep end, then it comes back to 5, then after it comes to 6, then after it goes back to 5, then to 7, and then it takes this other route until it will arrive at this 12 here. So as we said, it uses no prior knowledge about the problem. Then the breadth first search, it goes level by level, so it will move from 11 to 7 to 15 to 5, 9, 13 until it arrives at that point there where 12 is. So that's what we call uninformed search. It uses no prior knowledge about the problem. Then when we talk about the informed, this is guided by the knowledge of the problem. So under informed search, we do not waste time taking a route where we know that our answer may be in the alternative route. So if I'm looking for 12 and I'm using uninformed search, so there will be no way I can move from 11 to 7, yet I know that my 12 is here. So it will use a prior knowledge about the problem it is solving to enable it to know that I know I should take this route. And we have various algorithms you can use, as the hill climbing, the best first search. So when we talk about them, we didn't want to go deeper into these algorithms, being that this is not a video about algorithms and we have limited time. But best first search is going to combine both the advantages of the depth first search and the breadth first search. So it will go deeper, but if it identifies that the alternative path is closer to the answer it is looking for, now it will take the breadth path, and so on. So if you look about the hill climbing, of course it looks at the nearest, the neighbor, the best neighbor from where it is. Take an example that you are climbing a hill, so you reach somewhere and you see which next area to you is at higher altitude than where you are, so you go to that next part until you arrive at the maximum top of the hill, though each of them has its advantages and the disadvantages. So under problem solving by search, we can use either the informed or the uninformed. The informed, we normally sometimes call them the heuristic search, because we are having the knowledge about the problem that we are solving. So we estimate the cost from where we are to the final answer, and we take the shortest, the route that can make us arrive to that desired goal using the least cost possible. So of course in the Sugar Scout, it is using a heuristic search to prioritize treatment, management strategies based on the patient risk factors, as we said earlier. So that is it. These intelligent types, and what I'm not going to be focusing on them because of the limited time, so you can be passing through. Yeah. So if we proceed, we have the knowledge representation and reasoning. Yeah, that is our fourth module. We want to see knowledge representation. How can we represent knowledge? Yes, so because as you know, to solve any given problem we need knowledge, and that knowledge should be represented in a way that can be easily understood. So knowledge representation is simply the ways of representing knowledge. So we can have symbolic versus the connectionist ways of representing knowledge. When we talk about symbolic, and it will be our main emphasis, symbolic means that we are going to represent knowledge in form of symbols. I think you know what a symbol is. It can be a letter, it can be a digit, it can be a figure, it can be a shape, and so on. So look at this statement here. I have here Ibrahim is a student at MOOC, aged 23 years old. What do you get from such a statement? You get the knowledge that there is a student, and that student is named 23 years old, and his name is Ibrahim, and he studies at MOOC, Makerere University. But Ibrahim is not here. These are just symbols, but they are used to represent that that knowledge, that information. I think you can see there is an image here at the middle of my slide. There is an image here. If I ask you what is this, can you say that this is a duck? Or this is a house or anything else? No, of course it is just a symbol, a simple picture, but it is handling a lot of information. So this, we are talking about the president of the Great Republic of Uganda, but it is just a symbol that is representing him. So when you talk about symbolic AI, that method of representing knowledge, we are using symbols to represent knowledge. And what are the ways we use in the symbolic AI? We can use the proposition logic, we can use the first order logic to represent knowledge. We can use, of course, proposition logic. We use the statements. I think you know what proposition logic is. The statements that propositions, statement that can be either true or false. I can say 4 is greater than 3, for example. Kampala is the capital city of America. So you can say no, you are lying, or you can say yeah, it is okay. So those are what we call propositions. So you can say X and Y, or if X then Y. So those are propositions. I'm representing an information in terms of X and Y, symbols that are representing some information somewhere. I can use first order logic, where we have the quantifiers for all there exist and so on. So I can say for all X, given that X is a set of whole numbers, X should be greater than 0, something like that. An example. So the first order logic, it is not a video on first order logic, but I'm just showing you the different ways you can represent knowledge using symbols. So the computer or the model you are modeling in AI does not understand that patient you want to model. You are not going to get that patient, then you feed him in the computer. No, but you have to get the information about him, and you represent that information using any of the methods that we have here. And we have said we can use the symbolic, and where we are going to use the propositions and quantifiers. So take an example of this diagnosis process. So we can say if X, for example, X is representing the blood level sugars. So I say if X is greater than 20, then true. So that is meaning any patient whose blood sugar levels are greater than that given amount, it is true, that is positive, and so on. So we see that in the diabetes scout we have that rules like if sugar level is greater than X, X is a given value, and for example weight is greater than y, then risk is high. Some of the methods, so that is how we can represent knowledge and information that can easily enable reasoning. Of course, reasoning is from the way we are going to represent the knowledge from this first order logic. So it is going to reason that being that this blood sugar level is at this amount and this, so maybe this patient is positive or negative, something like that. Our next mode is about inference in first order logic. First order logic is that logic that is enabling the quantifiers, their exist, and the use of variables and so on. So in proposition we don't have variables. You cannot say that a is greater than 3 because you cannot assign a truth value on that, yes, unless we know the value of a. So but here we have the first order logic where we can have that, where we can have quantifiers, where we can have and so on, as you know that in the first order logic stuff. So here I want to see inference in first order logic. What is the meaning of the term inference? When you talk about inference, we are talking about deriving new logical conclusions from the given premises. Inference, we want to conclude. We have a set of given information, but from that we want to conclude. So for example, take a simple example. I say that if it rains, then the ground will be wet, and I say it rains. So I have two statements as my premises. If it rains, the ground will be wet, and I come to see that yesterday it rained. So I can conclude from those premises that therefore yesterday the ground was wet, something like that. So that is what we call inference, deriving new logical conclusions from the given premises. So under inference we have what we call the answer extraction process. This is the finding of the final answer from a knowledge base or reasoning base after reasoning or inference. So the answer extraction process, to find the final answer from a knowledge base after the inference, after carrying out the inference process or reasoning. So properties, under here we have some properties that are very crucial for a system if it is applying inference, if it wants to derive new logical conclusions. And of course each property is applicable to different modules depending on how you want your final results to appear. We have what we call soundness. If we say that an inference is sound, therefore it should derive only true values. If we say that anything is sound, an inference is sound, it should only derive true values. In other words, you should not have false negatives. Are they false negatives? True, because we have the true positives and the true negative, then the false positives. We should not have false positives. It should never derive an answer and it is said that it is positive yet it is negative. So wherever we say that the inference is sound, therefore all the values it should extract, they should be positive, they should be true. In other words, should never extract a negative answer. Then when we say that it is complete, therefore it should extract all the true values in the given database, in the given knowledge base. I think you get the difference between the two. Completeness, we want it to extract all the true values. Of course, take an example. I have a set where I have 1, 2, 3, and 4. And I say I want to extract numbers that are greater than 1, that are greater than 3. So that are greater than 3. Okay, I have a set of numbers from 1 to 10, and I want to extract numbers that are greater than 5. So when we say numbers greater than 5, we have 6, 7, 8, 9, and 10. So if a system extracts 9 and 10, I can say that it is sound, because all the values extracted are true. But it is not complete because there are some values it have not extracted, yet they are within the desired range. So under completeness, we can have some false positives provided that all the true values are extracted. So given the premises, and a system should be capable of deriving or concluding all the true conclusions, to derive all the true conclusions from the given premises, to say that it is sound, not to say that it's complete. Then it should never conclude a false answer if it is to be sound. As I said, that you can need your system to be sound or complete depending on the scenario you are working at. So the building blocks we have in inference, of course we have the axioms and the theorems. Our time, but okay, when we talk about axioms, these are just the basic rules in any given concept, and they are said to be true without any reference, without any proof, but they are just there to be true. For example, if I'm talking about probability and I say that the total probability should be 1, yeah, that is agreed upon without any proof. If I say you cannot say no, prove that the total probability has to be 1, right? Yeah, so that is what we call an axiom. Then what we call theorems, those are methods that can be proved. They are functions, or I can say equations, I call it whatever, but they can be proved using the axioms. For example, if I say that probability of A intersection B equals to probability of A plus probability of B minus probability of B, no, probability of A union B, as you know that rule, equals the probability of A plus probability of B minus probability of A intersection B. That is the theorem. So it needs to be proved using the axioms. So the axioms are that probability should be between 0 and 1. Here, that needs no proof. It is that the total probability should be 1, needs no proof. But for the theorems, they need to be proved using the theorems. So in simple terms, that is inference, just deriving a new logical conclusion from the given premises. And of course, in the Sugar Scout, as I told you earlier, our project, of course, you know that the facts we have that patient has high blood sugar. That is the premise. We have another premise that the patient frequently urinates. That is another premise. So we come to see that if symptom A and B, then diabetes risk is high. So we see that if a patient has high blood sugar and he urinates frequent at night, for example, then the risk is high. So we can say, yeah, this patient maybe is positive or is negative depending on the situation. Okay, now we have reasoning and uncertainty as our 6th module. Reasoning and uncertainty, we are talking about handling incomplete, noisy, or ambiguous data. So here we have incomplete. The data may be incomplete or noisy or ambiguous. So it is not direct that from morning or that we have 2 plus 3, but the data we have is incomplete. So we need to reason and we find a possible solution, but basing on data that is not complete. In other words, we don't have all the necessary resources that we should or we can use to derive the appropriate conclusion. So the causes of uncertainty, we have laziness. Maybe the data, all the necessary resources can be collected, but due to laziness, we cannot find the remaining sources that can enable us get all the necessary resources. Or it can be theoretical or practical ignorance. We can be that the theory cannot address that, or practically, even if we apply the true theory on that, again we cannot, again we will remain uncertain about the information, about the data that we do need. So how can we handle reasoning under such conditions? Of course, we can use the probability theory. Yeah, probability theory, as we all know it is about handling uncertainty. But here we are handling uncertainty about facts. The probability of being positive is 2%. The probability of being negative is 0.8%. We could not use probability if we are certain that this someone is positive or negative, but we apply probability when under the conditions of uncertainty. And here we can use the Bayes rule, as you know it. This rule, of course, it updates beliefs based on the evidence. I think you know that formula. Probability of A given B equals to the probability of B given A times the probability of A over probability of B. So we use such formulas to carry out reasoning when we don't have complete information, or the data is ambiguous. We cannot directly derive information from it. And of course we can use the Bayesian network. Yeah, of course it is another building block if you are talking about reasoning under uncertainty. How does it look like? It assumes that wherever we have two, for example, two nodes, under here we have nodes and edges. Wherever we have two nodes that are connected to each other, there should be a link between them, indicating the direction of the cause. So for example, from this our simple diagram, this means that A causes A causes C, therefore C is caused by A again causes D, it causes B. So this is a parent of A, and if again C causes E, so it will be an ancestor of A, and so on. So that's just the Bayesian network. It is a graphical representation, and we use this to handle reasoning under uncertainty wherever we are not certain about the outcomes. And of course, them combined, we can get what we call the utility theory. Utility theory, here we are combining the probability of things to happen, and we combine the logic. So we combine all of that, and we measure the desirability of the outcomes. We say we need this to be the outcome to be this. So no, being that there is this possible solution and this one, let us go with this one after measuring the desired outcome there. Okay, so our time. So that is it. Reasoning and uncertainty, we can use some of those to carry out that. We may have some examples, but time cannot allow us to do so. So let us pass through planning. We are planning just the reasoning about the future events to establish action sequences. We are reasoning about the future events. So I want to do this in the near future. So what can be taken to enable me do that in the near future? So we are reasoning about the future events so as to establish action sequences that can enable us arrive at our goal. That is what we call planning. It can be classical. Main methods, you can use classical or hierarchical. Under classical, we have the explicit goals that I'm from home, I want to arrive at the workplace. We have definite effects. Yeah, the effects are definite. For example, if I take a taxi, it should take me to my workplace. There is nothing like the traffic jam will be there. There is nothing like there will be an accident. So under classical, we are assuming definite effects. We have complete information about the environment and deterministic environment. So an example of the classical, we have the STRIPS, that is the Stanford Research Institute problem solver, where we have the initial state. We have we move from the initial state we were planning, but we have the initial state, the state in which you are currently. Then we check the available actions with satisfied preconditions. Of course, we have actions and you have preconditions. That to be able to take coffee, okay, you need to have sugar, you need to have water, boiled water, and so on. So we see that you want to take coffee, for example. Okay, our example, you want to go to the workplace, but the condition, for example, you need to have transport. If you have transport, then you can board a taxi. So now the available action here will be boarding a taxi when with the satisfied precondition that you have transport, for example. Then you add it to the list, and we have the add list and the delete list. Add list, this is where you add, for example, that you are from home. After the preconditions, you board a taxi and you arrive at the workplace. Now you add that at the workplace, and delete that we are from home initially, but you are no longer there. In simple terms, that the strips. We have the hierarchical planning, we have the abstract, the subtasks, and the primitive. Abstract is the general problem that we want to, the general thing that we are planning. So I plan to make a coffee. That is an abstract. But how are you going to do it? Then the subtasks, you break it into simpler tasks. For example, boiling water. For example, getting something to eat from the shop. So those are subtasks. Then the primitive, those are the tasks that can no longer be splitted further. So we start with an abstract. We keep on breaking it into subtasks until we find the primitive. Then after that, we keep on handling one by one. So planning, just choosing an action that moves from the initial state to the goal state. And of course, as you see in the Sugar Scout example, our initial state is the patient risk profile. Then the goal, we want to reduce the diabetic risk. The plan, we want to recommend that you can take this diet, you can have these exercises, and so on. Then after that, we can look at our module 8, and that is planning and decision making. As we have looked at planning, then we want to combine planning with decision making. Yeah, so here we said that we are combining planning with the utility theory and risk management. We talked about planning, we talked about utility theory. Of course, we know that. So now, planning and decision making. We plan and we have a lot of possible solutions that can be applied to the same problem. But now, how do you arrive at the decision and you take an appropriate solution among the given many? That is where we combine the two. And of course, we have a variety of things, of frameworks that we can use, but I decided that we go with the Markov decision process. And that, of course, under the Markov decision process, we have the states, the actions, the transition probability, and the reward function. When we talk about the states, state is not a new word to us right now. Then the action, the different operation that can be taken. Then the transition probability, the probability of arising to a new state given the initial state and an action. I'm at state S1, I want to arrive at state S2 by taking an action R. So what is the probability that when I'm from home and I board a taxi, I will arrive at a situation at state 2, and that is I will arrive at my workplace. So that's the transition probability. Then the reward function. Okay, we can simply visualize it from here. This is the Markov decision process. We have the different states, for example, S1, S2, those are states. Then the actions, we can see that boarding, board the taxi, you do this. It is an action that you can take to proceed from the state you are in to the other state. Then the transition probabilities, for example, here from S1 to S2, we have this. We have 0.7, that is the probability that when you board a taxi will arrive without the traffic jam and so on. So we can use those different frameworks to come out with the decision making. Yeah, I want to summarize. Of course, time is not on our side. So our last module is about machine learning, and this is about building computer programs that learn automatically from experience. Of course, we have mainly the two approaches. We have the cognitive and the engineering approaches. The cognitive, of course, this is about modeling human mind, machines that can reason and think the same as the humans do. But with the engineering approaches, we just consider the outcomes irrespective of the method that we use, and that is the applicable process right now, applicable approach. Just modeling machine that can learn through experiences, not necessarily as the humans think and react. So here we have different types of machine learning, where we have the supervised, unsupervised, and the reinforced. Supervised, now the machines learn through using labeled data. So we feed in data that is labeled, so the machine learn using that data. Then unsupervised, there we have the classification, the regression. Classification, we are just finding groups, and regulation, we want to find the value. Yes, so the machine classifies here groups, then there it finds the value, continuous value, that is under supervised using labeled data. Then unsupervised, we are using unlabeled data, where we have clustering and association. Then the reinforced, that is through interaction with the environment, where we have rewards and penalties. So if a machine arrives at the correct answer, it is rewarded. If it arrives at a wrong answer, for example, it is penalized, and so on. And in that process, it is going to learn. So specifically, basically, that is it. Our 9 modules summarized as simple as we could, so that we can beat the time factor. Thank you.